We're going to begin section 7.3. It's still trig, but the title of this section is Trigonometric Substitution. Okay. So, can I erase this board here? Okay, I'm going to erase all this and title 7.3 Trigonometric Substitution. What happens in this section? You get a lot of stuff that's written like this, maybe inside integrals. You get stuff like this. I'm going to write stuff. Maybe something like this. Okay, or maybe something like this. These are the types of situations that will occur inside the integral. You go, well, how do you deal with that? We can use trigonometric substitution. Well, there's a cool table in the book. I'm actually going to present it right now. I want to let everyone know what page this is on. This is from page 478. All right? It's really very simplified. Trigonometric situation. This is the kind of stuff that's going to appear in the what? In all the integrals. You know, maybe integral dx, integral dx. I want you to see how you could recognize when am I going to need to use this section? Because the last section also had what in the title? Trigonometry, right? So I wanted everyone to be able to say, when am I going to use this section? You see things with these radicals, and maybe it's like x squared and x squared. And y'all notice the other perfect squares in there? Okay. So I'm going to draw triangles. Here's my first triangle. I'm going to put an x here and an a here. I'm going to write this as square root of x squared minus a squared. That's by Pythagorean theorem. Does everyone agree? If you see Pythagorean theorem, that would come out like that. That's the first case you'll see in this problem. And when you have something like this, what we're going to let x equal to? Oh, and put a theta here. I apologize. I'm going to put a theta there. What do you notice about sine of theta? Can everyone see that triangle? I'm going to write it really big over here. Theta. This is x. This is a. This is the square root of x squared minus a squared. What do you notice about sine of theta? It's a over what? So what would x equal? X would equal a sine theta by so-called toe. Do y'all agree? Okay. Sure. Do you agree here that the sine of theta would be opposite over hypotenuse? Oh, cool. So if we get a scenario like this, we won't see triangles, but you'll see this expression somewhere. We can always just let x equal to a times sine theta. Now the reason is because what's sine of theta in a scenario like that? Opposite over hypotenuse, so a will just equal x sine theta. Cool. And I'm glad you asked it, because I want you to think like, there's a way you can just kind of make these drawings and just do Pythagorean theorem and so katoa, right? I know. Here's another scenario, and I'll make sure to put this over there too, so it's sitting up there the whole class. Well, what if you get something like this, and you get an a here, right? And in this case, you have the x there. So you have an a here and an x there. Well, with this case, make sure I have that right. Oh yeah, I'm going to put a here, x a, x will equal. Let me make sure everyone sees this. Sine theta equals a over x. So in this case, I'm going to rewrite this because that wouldn't work out, would it? No. So I'm going to draw this again. I'll make a nice prettier triangle here. Right here. Yep. And I'll write the actual chart that they have. A squared minus x squared. I'll draw the triangle last. So no one's confused. We're going to use x equal to sine of theta. Alright. If you have a scenario like square root of a squared plus x squared, we'll let x equal a. Okay. And finally, if you have square root of x squared minus a squared, we'll let x equal a secant theta. And I'll leave some room here. In this table that I'm presenting here, you'll notice is on the textbook. It's in the textbook on page 478. I apologize for that last triangle. I want you to see these do involve triangles. So in this first case, sine of theta would equal x over a. So this would be square root of, by Pythagorean theorem, b squared plus x squared equals a squared. So what would that b squared equal? Square root of a squared minus x squared. This image goes with part 1. But you could check it over. So I don't see that the sine of theta equals x over a in that scenario. I'm going to write the triangle backwards. This section is not bad at all. What we're saying is that when we see these integrals with these radical expressions, this is the substitution we're going to follow along. We're going to follow along and use this substitution here, this substitution here, this substitution there. But I wanted you to see why, because this triangle, sine of theta is x over a. What would the triangle look here? Can you help me build this? Here, put a theta there. Well, tangent theta is, what would tangent theta equal? X over what? X over a, so what would this become by Pythagorean theorem? A squared plus b squared equals c squared, wouldn't you get that? And lastly, what would this triangle look like? I'll leave these triangles up here the whole time. And when x equals a secant theta, so what's secant of theta equal to? X over a. Remember, secant is cosine's reciprocal buddy, right? So when I do secant theta is hypotenuse over adjacent, I'll put x here, a here, and put the square root of x squared minus a squared. And put the theta here. But these triangles were not drawn in the textbook on this page. 478. But I encourage you in your notes to put those triangles, because they're all related. There's something else I'm going to add at the end. If anybody's looking at a textbook now, you go, hey, they wrote something else here. I'll add that in a second. But those are the three scenarios. So obviously, when we see this in the integral, this is going to be our substitution. If I see this somewhere, these a's are constants. Please note that the x is the variable, the a is the constant. Cool. All right. We got it? We got it. Let me squeeze through here. All right. Well, let's get started. Let's look at a problem, everyone. This is from section 7.3. This is like number 1. Let's start off with a problem that's just like number 1. And I got the integral of dx over x squared square root of 9 minus x squared. and they want us to find the antiderivative. All right, so this is like number 1. Can you recognize which scenario it is? Man, you're good. So as long as we know this, these 3 situations here, if we're familiar with these 3 situations, when we see that radical expression that appears in the integral, we'll know exactly which one to use. So I'm saying here, that's a 9, so the a value will be, is a 9 or a 3? I'm going to let a equal 3. This is looking like this scenario, scenario 1, and I'll let x equal 3 sine of theta as my trig substitution. Okay, so I'm going to write that down. Let's let x equal 3 sine theta. Cool. Hey, real quick, what would dx be in terms of differentiating both sides with respect to theta? This is the first thing I'm looking at for this problem. Let x equal 3 sine theta. What is dx equal? 3 cosine theta. And what do I have to put here? D theta. All right. That's the first thing I'm going to check that off. I just want everyone to realize that. I know I'm going to let x equal 3 sine theta, but then dx would equal 3 cosine theta d theta. Great. Well, the second thing I wanted to look at is this funny radical. So let's write it again over here. And let's substitute. So I'm going to call this part 2. Before I go back to the integral. What would now the square root of 9 minus x squared become? Square root of 9 minus x squared now becomes, what can I substitute for x? This 3 sine theta. So you get the square root of 9 minus 9 sine squared theta. And I need you to help me simplify that. Everyone so far so good? How I put this here and substitute it? Yeah? Oh, yeah. So first of all, and hey Nicholas, you were okay with this part, right? Yeah. So now what I want to do, on each one of these problems, once I took care of whatever the x substitution is in dx, I want to find that radical part, whichever part it was, write it separately, but then use what I just used as my substitution and substitute for the letter x. This one right here. So this will become, I'm just going to put this is equal to square root of 9 minus, but for this x, I'm substituting the 3 sine theta, and then I got to square it. So a 3 squared becomes a 9, and then a sine of theta squared becomes a sine squared theta. So far, so good? Now, can you help me get this thing cleaned up? What can you factor out of that? Nice, I'm going to write that. We're just going to play with this. Factor out of 9, you're left with. See, eventually, on every one of these problems, you're going to be able to eliminate the radical. You're always going to be able to eliminate the radical. Okay. Someone I know sees something. Does this look familiar? I was up on the board like 10 minutes ago. That's just cosine what? Cosine squared. Okay. Oh, it's getting better. Everyone, can you rewrite this without a radical? What is that? 3 cosine theta. Hey, I'm going to write it like a true math geek. I'm going to write 3 absolute value bars cosine theta. I know. But we can take off these bars as long as we talk about what theta is. Does anybody know where cosine's positive? Which quadrants? You know, all students take rec. I'm just curious. All students take rec. I don't want, everyone, we're going to do this integral. None of us want those bars there, right? All right. Yeah, I know, all students take rec. But where's cosine positive? Okay, all students take rec. But quadrant 1 and quadrant 4. So the author did put a little note over here, and he said, hey, let theta only be defined for from pi over 2 to negative pi over 2. I just did, when I wrote, I didn't want to write this at first, because I thought it might bug you. This is written here because now we can take off these bars and say, oh yeah, cosine's always what? Positive. Does everyone see? I eliminated these bars because cosine theta is positive when it's in what? Those quadrants. So I'm going to write this for theta, or I'll write for theta less than equal to pi over 2. But the good news is you don't have to worry about writing this. It's just, we know that's part of the situation 1 here. Here, call this situation 1. And now it's ready. And when it's time to have some fun, you ready to substitute? What are we going to substitute for that square root of 9 minus x squared? 3 cosine theta. What are we going to substitute for this letter x? 3 sine theta. What are we going to replace that dx with? 3 cosine theta d theta. So this is interesting. We're getting everything in terms of thetas, aren't we? This is called the trig substitution. So I'm going to get this ready. All right. Start out with the top. What's in that numerator? 3 cosine theta and a d theta, right? If you want to put the d theta out here, I don't care. What's that x squared become? Look there. Well, first I'll write it like this, so no one's confused. All that, you got to what? Square it. Some of you squared automatically. You're really good at that. And what replaces the square root of 9 minus x squared? Just the 3 cosine theta. Ta-da! Now the game is just simplified, right? And let me check it over. I didn't screw anything up, right? I made there's 2 screw-ups today. I screwed up that triangle and that. This would be strike 3. Is that right? dx is what? 3 cosine theta d theta. That's my x. This is 3 cosine theta. Yep, you do not put the bars. We're not going to put those bars. We just know that this was going to be positive for this scenario. Now, help me simplify this. Stuff should cancel.
3 cosine theta.
Knock them out. Want to bring that 3 out in front? Or is it 3 squared? Please, 3 squared would be 1 what? And we're closing in on the answer. Boy, did that get better. Is that the power reducing identity? No, because it's in the denominator. Can I get that up in the numerator? I'm trying to do this integral. Is it cosecant squared x theta? Reciprocal button? Okay. Now, what's that integral? Don't worry, I know, that's why I want you to get familiar with it. This is negative cotangent theta, isn't it?
Sure. Where did the 1/9 that came out?
Oh, so that 1/9, what
sorry.
happened here, that's okay. That 3, that sine squared stayed here. I took that 3 and squared it as well. And it was in the denominator. I know these 2 3's canceled, but that 3 squared there made that 9 there and that
Oh,
denominator right there.
so you guys it was dividing 1/9 and you took that up. Okay.
That's right. And feel free even, if you want your notes, to put that, because you might look back on this like later tonight or tomorrow, and you'd be like, wait, that was a 3 squared, and then make that 9 there. That might look better. Just in terms of, going back and studying.
I believe button. Just press the I believe button.
I believe. And when that's negative cotangent theta, this thing is done. Except for one thing. The original problem had thetas or x's. So there's one more thing we have to do. This is where this comes into play. All right, so I need us to kind of look at this triangle to rewrite things. So you can look back at that. But these triangles are important. Now the author didn't have these triangles there. That's why I wanted you to put these triangles in your notes there with each situation. We got to put everything back in terms of letter x. But this is the beauty of this elegant method here, everyone. Although it was limited here before, now we're going to have everything back in x's, and we're going to have the actual antiderivative of this expression. So let's start out. Negative 1/9. Look at that triangle. What the heck is the cotangent of theta? Tangent is opposite over adjacent, right? What's the cotangent of theta in that triangle drawing? Adjacent over opposite, right? So katoa, but I'm doing tangents reciprocally. So adjacent over opposite, I can replace this cotangent theta with square root of, now what was a again? 9 minus x squared all over x. Plus constant. Ta-da. You just want to put that 9 with this. Does anybody want to do that? The author does that. How does the author write this? It looks a little better. He just writes 9 minus x squared, and he just puts a 9x down there. Let's see, that's the actual antiderivative. Anybody use Wolfram Alpha? Okay, cool. Go, like home tonight, go. Type that in. See if you get that expression. Now right now you're like, do I have to talk about theta anymore? Because it was here? No, because we put everything back in terms of what? X. Now, this thing's fine as the antiderivative. It may have a limited domain there, because it has a square root. But we're good. Man, you all are awesome.
Is there going to be any case where we might end up with a radical, say, on the denominator? We're going to have to do like rationalization or something like that.
No.
Those kind of problems.
The only thing, we'll look at different scenarios. The only thing that might come up that's weird, you won't have to do that. But when we do this substitution, you might just get something like this. Like, you'll finish out the integral here like this. You might go, oh, the antiderivative is just theta. But you and I are going to go, how do we restate theta? And we're going to have to think of that as, oh, we got to think of an inverse trig expression for it. That's all. Okay, well, let's try another one. This time, well, we did one of these. Let's look at something that has this. What if you got an x squared minus a squared? This is like number 3. Okay. Number 3. They got an integral. And when they had a 4, I'm going to change it to a 16, okay? This time, this is up in the numerator. And they have this in the denominator. This is a x and then a dx. Ooh. Erase that. Leave all the triangles. Erase all this. But let's do a situation 1, situation 2, just like we did before, and get this baby rolling. So beyond this section, later on in this course, you bet, it's like if you see these funny integrals with x squared minus 16s and x squared minus 9s, or x squared plus 9s, or x squared plus 25s, or 25 plus x squareds, we know we can use this section to solve the problem. All right, situation 1. Which one of those 3 is it? X squared minus 16. It's this one, right? What should I let x equal to? I should let x equal a secant theta. But what's a here? 4 secant theta. And we're talking about this triangle right here. The a is a 4. What would dx be? What's that derivative? 4 secant theta, tangent theta, d theta, right? Cool. And if you need to update your knowledge on these trig identities, number 1, or the trig derivatives, just take some time this weekend. Look at the trig sheet, make flashcards, stuff like that, whatever it takes to really get these down. All right, we took care of the x and the dx, but you're done, but I need to do something for this radical, right? All right, what would be this? So what do you replace an x with? All right. This should work just like the last problem. So some of you, I know these first ones I'm doing every step. I bet you during tests, some of you can do like 3 or 4 steps in your head. This becomes 4 secant theta squared minus 16, which becomes the square root of 16 secant squared theta minus 16. Can you factor? What trig identity emerges? Secant squared theta minus 1? I'm showing every step here, but I bet in a while, some of you be doing like, when you do part 2, you might do 2, 3 steps in your head. What's this become? Square root of 16 times a trig identity? Tan squared, outstanding. Okay, I'm going to do it like the true math geek that I am. This is for absolute value of tan theta, but I don't want to put those bars. You're not going to put the bars, so let's define theta. All students take crack. Where's tangent positive? Quadrant what? 1 and quadrant 3, so now I'm going to rewrite this as 4 tangent theta, and I want to show everyone what they wrote over here. For this scenario right here, they said, oh, theta goes from 0 to pi over 2, and now I'm going to do the third quadrant. Whoops, let me make sure I get the higher here. My apologies. And I'll get out of the way. Pi over 2 to 3 power 2. I can put an equal on a 0 though, can't I? Isn't a secant of 0, 1? Secant of power 2 is undefined. I don't put an equal sign there. Secant of power 2, that's undefined. How about the secant of 3 power 2? That's undefined too. So I'm just going to put an equal on a 0 because it's equal to 1. So I can remove this if we know that theta is for what? For theta, really, what quadrants? What quadrants? In quadrants 1 and 3. But I did want to point out that this is actually written in the textbook, in the table. This part right here is in the table. I wanted you to know, everyone, why I can take those bars off. That's why. Because it's defined for just those 2 quadrants. So we're ready to roll.
I'm sorry, could you repeat that? So T is for tangent A, Y.
Oh yeah, this is basic trigonometry. All trig functions are positive in the first quadrant. Only sine is positive in the second quadrant. Tangent is the only one and it's reciprocal but in the third quadrant. And cosine is the only one positive in the fourth quadrant.
Okay.
But that's the the mnemonic device. All students take, I say crack, but it's mostly all students take calculus.
I thought it would crack. Okay.
All students take cookies.
No, crack.
All students take charge. Everyone, I'm ready to substitute. We don't have to put those bars. So I'm going to take off this. What's this become? Just a 4 tan theta, right? Cool. What replaces the x? 4 secant theta. And what replaces the dx? 4. This dx, by the way, is up in the numerator. 4 secant theta, tan theta, d theta. I was able to squeeze it all in there. That's the 4 tan theta. This dx is 4 secant theta, tan theta, d theta. And that's a 4 secant theta. Anything cancel? Whoosh. Whoosh. What do you now have? 4 tangent theta squared. Is the integral of tangent squared just secant theta? I don't want you to get stumped on a test here. You go, oh, the integral of tangent squared, that's just something simple. It's like, well, hold up. This is something simple. The integral of that is what? So how am I going to finish that up? We've got to use something from the last section from relative to this. Yes, they're using a trig identity, replacing this with secant squared f theta minus 1. Right? Oh, let me put that 4 out there. There was one. These 4's cancel, but he says, don't worry, don't forget about that 4. But now, can I write this as 2 separate integrals? Minus a. Can I do that? And what's the integral of secant squared theta? Tangent theta minus, what's this? Now, do you want to keep that 4 factored out of the whole thing? You want to do that? Leave that 4 just factored out, right? Tan theta minus theta. We just have one more step to do though. How are we going to get everything back in x? That's right. Just go back and resubstitute. All right? So you're all right? Remember, you can factor out the 4 if you like the factor. We can leave the 4 there, but I'm going to resubstitute. What's tan theta equal to? Where's the triangle? Because I'm looking here, maybe it doesn't help, right? You might see it right there. You might see it right there, but you might just look at the triangle. So what do we have here? 4 tan theta would be 4 times x over y, right? What was that? So far, so good? That was tangent of theta was equal to square root of x squared minus 16, right? So tangent theta, x squared, square root of x squared minus 16, when you're looking at that tangent theta, can we just say in this case, oh, I mean, which triangle am I looking at? You guys are the best. Oh, I want to look at the wrong triangle. It's this triangle, let me rewrite it, or highlight it. What is tangent theta? Square root of x squared minus a squared over a? What was that? All right. Now this. I'm going to have to use this, so I'm going to think of an inverse trig function. So I'm going to rewrite theta as, there's theta, inverse secant or arc secant of x over a. And what was the a? 4. Remember, you can factor out that 4 if you want. What happened with these 4s? So let me write this final answer again. I now have x squared minus 16 minus 4 inverse secant of the x over 4. Awesome.
How'd you get inverse secant for when you decided on it?
When I looked at this one, and we're using this triangle, right? There's two ways you can do. You can look at this triangle and go, I need to replace theta. Well, secant of theta is x over a, right? Secant of theta equals x over a, so inverse secant, you know, theta would equal inverse secant x over a. There's something else you might look at that's better. You might just look at that. So I'm going to just go like this. Come outside here, and Andrew, what would that be? X over 4 equals what? Secant theta. Now rewrite that as theta equals. What would theta equal? Inverse secant of the x over 4. You might find that easier. I just like people to know there's triangles involved, aren't there? These triangles aren't drawn in the book. Sometimes it's just easy to look at that triangle and go, so katoa. But Andrew, you might have found that easier to think of how I could get that theta by itself. Cool. Awesome. Nicholas.
What's the question how you got this, the second one down, so 4 tan x, 4 secant tan.
So 4 tan x, 4 secant tan x in terms of the thetas?
How did you find that? Yeah.
So here, were you okay when we let x equal 4 secant theta at the beginning?
Yeah.
And then I differentiated to get the dx. So you and I knew what we're going to substitute for this and that x. But then we did a square root of x squared minus 16. We noticed that turned this. So now it became substitution time. So for the letter x, I substituted this, right? And that went right here. And then for this whole radical, I substituted, it's way at the end. And Nicholas, I know I took 1, 2, 3, 4, 5, 6 steps to get this. You might find yourself, after doing a few of these, you're getting this written in like 3 steps. Because it always plays out like that. Cool. And then lastly, the dx got replaced by that whole mess. Oh, of course. And when I thought it'd be great right before you leave, can we do this other scenario? Awesome. Let's do this last scenario. All we need is one of these. Gotta put stuff down. So, everyone, for our last problem, what do we got? Let's say we got the integral of, we just need one like situation 3. How about like number 9? So this is like number 9, and I get the square root dx x squared plus 4. It's funny because that looks like something we've done before, but it isn't. Is that like an arctan or something? Hey Nick, off your question. You had a good question there. I always do like part 1, part 2. Feel free to think of it as part 1, part 2, part 3, because there's usually a dx, an x, and then this square root thing. And when I recognize this is a trig substitution, anybody know what I should let x equal to? You got it. 2 tangent theta. That's a 2, that's an x. So I'm going to let x equal 2 tangent theta. because of this. All right, what's dx? Was everyone okay with this? It was by recognizing it, okay. Now what's dx? Yeah, the derivative of tangent theta is secant squared. Okay. We're getting ready for our trig substitution. One more thing. What's this equal to? Now at this point, you might start getting really fast. But I'm going to write out every step again. And Nicholas, I want to point out I let x equal that 2 tangent theta. Okay, I just differentiate to find out what dx. Now I'm going to figure out what this is. So for that x, I'm going to substitute that. This comes in here. What's a 2 of tangent theta? And then I got to square that. 4. Was everyone okay that I squared the 2 and the tangent squared there? All right. Can I factor? All right. Anybody know what trig identity for tangent squared theta plus 1? Secant squared theta. Here I come, the math geek. This is equal to 2 bar secant theta, but in terms of this, what do we get there? I got 4 tan squared theta plus 4. 1 plus tan squared equals secant theta. And when where is this positive? First and fourth quadrant, right? Cool. So I'll write this again. The only thing is when I write this one, and when I'm not going to put equal signs on the pi over 2's. But you were right. You said first and fourth quadrant, right? But I want to secant of pi over 2 is undefined. So I would just say, this is 2 secant theta with theta from pi over 2 to negative pi over 2. This is quadrants 1 and 4. And again, that's why all students take crap. We're saying cosine is positive. All trig functions positive here, and cosine is secant's reciprocal, buddy. But hey, everyone, this is included in a table on page 478. I didn't write these at first because I knew when I was a student, I'm like, what the heck is this junk? And I never figured out why. You now know the why. It's so you can get those bars off there. That's why. Right? But now it's good to go.
Thank you.
What's going in for our substitution? What replaces the dx? So I'll put this here. Nicholas, I noticed something. Last time I put something for an x, there is no x in this problem. So the only thing I'm left is replacing something for this, which is the 2 secant theta. All right. This is too good. What happened to the 2's? But we do have to talk about that. It's a great problem to finish up on today. And when you know how to get the integral secant of theta, you've probably never done it before. It requires a manipulation. All right? If you read in the book, they have like a little formula in this section. I didn't think you have to memorize it. To integrate the secant of theta, believe it or not, we've never done that before. We've done the integral of cosine theta, right? We've never done the integral of secant theta. The trick is, it requires a little trick, and I'll introduce you right now. We're going to multiply the number 1 on top and bottom to this expression. All right? And this is what we're going to do. We're going to multiply, in order to integrate the secant of theta, we're going to multiply secant theta plus tangent theta over secant theta plus tangent theta. Now when I have to just halt so everyone understands what I'm doing. I am doing this so we can integrate this stupid thing. Right? So I'm multiplying the number 1, isn't that by the identity? Right? That's identity property, this is a 1. But this, the reason I'm doing this will allow us to get this integral. It's a manipulation trick. It's explained in the book, but if you looked in the book, you might think, oh, I got to memorize a formula for the integral of secant theta. Bogus. No, just know to do this little trick. So when you notice what you have now, what's in the numerator? That was that trick to do this. You've got a what? What's that times that?
Secant squared.
Secant squared theta plus secant theta, tangent theta. And what's it all over? All over secant theta plus tangent theta, d theta. This requires a use of. This requires a use of, everyone. Guess what we'll let u equal to? Let u equal secant theta plus tangent theta. And this thing will work out perfectly. Guess what du is? What's the derivative of secant theta? Secant theta, tangent theta. And what's the derivative of tangent theta? Secant squared theta. Now I put my d theta. Y'all see what happens? Now this is beautiful. What gets knocked out in the numerator? This entire numerator becomes a du, and the denominator just becomes a u. Isn't that cool? That is so cool. So I don't memorize this. You can if you want. But I think I see it coming, Andrew. It looks like an ln. Looks like we got a natural log coming up. That's what's going to be the answer to this. So I get the integral of 1 of u is the natural log of u. Can we put our u back? What was u? Secant theta, tangent theta. Is there anything else, though? Look back from the original problem. What was the variable?
X.
X. Nicholas, were you okay with that? Cool. I don't want to rush anybody. You can look back and look at this stuff. It was funny. We would have been done here if this was easy. Oh, secant theta, not so easy. But we've got it right now. Now let's go back and put everything in. What can I replace secant theta with? I just used a triangle. All right, I gotta make sure I use the right triangle. What is triangle? This one. All right, on this triangle right here. That's a nice little A right there. What is the secant of theta? Natural log of secant theta here would be square root of x squared plus 4 over 2. What's the tangent of theta in that triangle? And when I'm using this triangle right here, right? What's the tangent of theta there? X over A. Opposite over adjacent. X over 2. And plus a 1. Did you all just want to combine that and do a plus over 2? You can. There it is. Isn't that cool? Of course, there's another way to use secant theta. You could have said 2 secant theta equals this, right? I just like to look at the triangles. Super duper job today. That's 7.2 and 7.3. Hey, stick around if you got any questions on this stuff. I think you need a picture of that. I will not erase it. Everyone okay? Everyone, have a great day. I'll see you tomorrow.